Hi, and welcome to this video titled Area Between Curves. So in the previous video or the previous lesson we looked at calculating the area under a curve, between the curve and the x-axis. What we're going to look at now is having multiple curves and finding the area enclosed between those two curves, or lines or functions in general. So there's a couple of ways we can calculate the area between two curves. We can use the difference between two areas, as you would if you were looking at the area of a rectangle. So for example, if we had an area like that, and another area here, and we wanted to work out the area in between those two shapes, we would find the area of the large shape, the area of the smaller shape, and subtract them from each other. So that's one way that we can work out the area between the two functions. The second, when we're doing that, we find the integral of the first function, find the integral of the second function, and take one away from the other, just like we did when we found area under curves. We can also use the area of the difference function. Okay, so in that case we use the intersections of this new function. They correspond to the zeros of the difference function. So if we just like we've done here, this is the first one. We have two separate functions. We find the area between a and b and subtract the areas. If we just subtract the two functions from each other and then find the integral, we get the same area, or the same result. So here we've got two functions. We can either find the area under gx, we'll find this area here, subtract it from this area, find this area, subtract from that, or we can use the difference, so we can subtract those two functions together. Gives us a new curve, but the intersection points correspond to the zeros of those of that new difference function. This will probably become a bit clearer when we do an example. So we're going to look at finding the area between this quadratic, x squared minus 6x plus 13, and x minus y plus 3 equals 0. So in this form we can rearrange that to y equals x plus 3, which is going to give us a straight line. So again, the first thing you do when we got these two equations or two functions, graph them, see what we're dealing with. So the blue line here is our straight line, the red is our quadratic, and we can find the intersection points. Again, we could find this algebraically, but it makes a lot more sense to just use graphical methods. So plot these on your graphics calculator and find the intersection points between those two functions. So here we're going to find the area enclosed in this area between where x equals 2 and x equals 5. So I said I'm going to go and show both ways of doing this. There's two ways. I'm going to show you both. First is the difference between the areas. Now again, we're going to have two areas, area 1 and area 2. Area 1 is going to be the area underneath this straight line between x equals 2 and x equals 5, and the x-axis. So basically this area there is what I'm going to calculate first. Second area is going to be the area under this curve, so between this curve and the x-axis, and x equals 2 and x equals 5. So we're going to get a large area, subtract this small area, and the leftover, or the remainder, is going to give us the area between those two lines, those two curves. So the area between the curves is going to be a1 minus a2, and we can rearrange that function as it was given in the question to be more like what we expect it to be, y equals x plus 3. So we've got our two areas here. Area 1, just find the integral of x plus 3 between 2 and 5. And this part from now on should be fairly familiar. We work out the definite integral and we come up with a value 39 divided by 2. It's positive, it's above the x-axis. Likewise for the second area, we find the integral of that quadratic between x equals 2 and x equals 5. Substitute our values in and we get an area of 15. So we've got our two areas, one being 39 divided by 2 and the other being 15. And the area between those two curves is going to be that first area minus the second, which will give us 4.5 units square. So again, the key, make sure we draw this diagram or graph this so we know what we're dealing with. We know that in order to find this area here, we're going to have to find the area of the line first and subtract the area underneath it. Now the second method, and it doesn't really matter which method you choose, it really comes down to personal preference and what you get used to. The second method is to use the area of the difference function. So again, using the same functions, I'll rearrange this to y equals x plus 3. And so the difference function is going to be the first function minus the second function. And it doesn't matter which order we do this in. So x plus 3, which is our first function, minus x squared minus 6x plus 3. Now remember that minus applies to everything in the bracket, so if we expand it out, x plus 3 minus x squared minus plus 6x minus 13, group the like terms, and we get negative x squared plus 7x minus 10. What we're interested now in is graphing that difference function. So here we have it over here on the left. We've graphed it, and our zeros, or our x-intercepts, are at 2 and 5. Remember up here, our intercepts were at 2 and 5. They correlate to our intercepts, our x-intercepts on the difference function. So now we can just go ahead and find the area of this area underneath this curve, between the curve and the x-axis, between 2 and 5. So yeah, you're just using the definite integral between x equals 2 and x equals 5 of that difference function. Find the integral, substitute x equals 5 and x equals 2 in, as we normally do when we have our definite integrals, and we come up with that same area. So the area is 4.5 again. So there's two methods you can use. Doesn't matter which one you use. The key is make sure you draw a diagram to start with, so you know what the areas that you're looking at, what the enclosed area looks like, and if you want to subtract areas from one another, which way to do that. Second method, do the difference. Make sure you get it correct. So make sure you are subtracting everything that's in that second function. So expand it out. Plot that as well, just to make sure that it's not coming back up again. So it's all, the same rules apply when you're looking at area under a curve. If it's above, it's going to be positive. If it's below, it's going to be negative. So we need to draw that graph to know what we're dealing with. Second example goes a bit further, so finding the area between the curves. So we've got two curves here, two quadratics, and some vertical lines, x equals negative 1 and x equals 2. Now if we just put all that onto a graph, we get a graph similar to this. So we have our two quadratics here, and black is x equals negative 1 and the red line is x equals 2. And we want to find out the area enclosed in between these curves and the lines. try and do it as neat as I can. That's the area we're going to look at. Now you can see, now that we've graphed it, find the area of this quadratic and subtract the area underneath this quadratic. That's going to give us that enclosed area between those two values. So we're going to use the area between two curves method. Area 1, area 2. So just simply in between x equals -1 and x equals 2. So to find the area between those curves, it's going to be the area of that first one minus the area of the second one. Find the integral for both functions. Subtract x equals 2 and x equals -1 into both of those integrals, and we should work out that the area between those two curves and x equals -1 and x equals 2 is 27 squared units. So again, a little bit more of a complicated shape, but once you draw the graph, once you determine what that area, enclosed area, looks like, it makes working out what areas to take away from each other that much easier. Okay, so always start off by graphing it, working out that area to be calculated, generally it's the enclosed area, and then work out which method you want to use, either the difference in areas or the difference in finding the difference function and calculating the area based on that difference function. Either one doesn't make a difference, you still come up with the same answer. So that is area between curves. I hope you found it useful. What we're going to move on to shortly, or the next lessons, is applications of calculating the area under curves, which we're going to look at next week.